Good evening, everyone. Is my screen visible? The slides are visible. Can someone confirm?
Yes.
Okay. Okay. I'll just wait for 1 more minute and then we will start the class. I'm just waiting for some more people to join. So, good evening, everyone. Welcome to the NPTEL online course on water and wastewater treatment. So, currently we are in week 3. So as you all know, the course instructor for this course is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So I hope you might have gone through the contents or the lectures shared for week 3. So in this week 3, we have basically dealt with the remaining water quality parameters, focusing on the total suspended solids and pathogens. And then we started with the treatment schemes. So first we looked into the preliminary treatment where we learned about the basic principles of bar screens and the grid chamber. And then we moved on to the primary treatment where we learned about the sedimentation basics and what are the different kinds of settling like the discrete and the flocculant settling. And then we learned more about the details of primary sedimentation tank. So this was the brief overview regarding the week 3 lectures. So today I have some objective type of problems, both theoretical and numerical, regarding these concepts. And also, if time permits, we will solve some subjective type of problems in the end. Okay, so let us start with the objective type of problems. So this is the first problem for today, which says that yeah. So this is the first problem which says that what type of settling do the blocks A, B, C and D denote in the figure below? So we have different types of settling. So you have to tell me which of these blocks represent what kind of settling. Okay. So whether it's a zonal settling or discrete particle settling or compression settling or flocculant settling. So you can write in your answers in the chat box whichever option you feel correct, and then we will discuss. So please try it out. I request everyone to take part so that we can have a fruitful discussion.
Sir, answer is B.
Answer is B. Okay. Anyone else? 1D. Okay. So I'm getting mixed answers here. B and D. Any other answer? D. Okay. So more people are saying it as D.
Yeah, D is the right answer, sir.
Yes. Yeah. So D is the correct answer actually. So if you see the first block, that is A, you can see the individual particles, okay, separately. So we can call it as a discrete particle settling. Okay. And then in the second block, you can see that some particles are coming together and forming flocks. Okay, so this will help them in settling efficiently. And then C, it represents the zonal settling. And then D, we when the concentration is too high of those particles, then we call it as a compression settling. So this is the brief description. So in discrete settling or type 1 settling, we see the particles settling individually. Okay, so without any interaction with the neighboring particles. So in this type 1 settling only, the Stokes law is actually valid. So to calculate the settling velocity of a spherical particle, like that. So in this type 1 settling only, the Stokes law is valid, where the particles settle individually without the influence of any neighboring particles. Whereas in type 2 or flocculant type of settling, these particles come together, okay, uh, to form flocks, so that the mass will increase and they can settle at a faster rate. Okay, so this is type 2 or Falkland type of settling. Then we have hindered or zone settling, which we call it as type 3 settling. So here the mass of the particles tend to settle as a unit, with individual particles remaining at fixed positions with respect to each other. So at different zones in together it will settle, okay, throughout the region. So it is called as hindered or zone settling. And the fourth one, which is called as a type 4 or compression settling. So here the concentration of particles is too much, such that they they influence each other and they try to compress or compact the structure. Okay, so the compaction of the structure happens due to the high concentration of particles. So you can see in the D block, we can see so much of concentration of these particles. Okay, so these are basically the four different types of settling that happens. So in the treatment, in the wastewater treatment process, we have different kinds of units, like the primary sedimentation tank, secondary sedimentation tank. So in different type of tanks, we may see different type of settling. Okay, so we will discuss it while going along the course. Okay, I hope this is clear to all of you. Let us move on to the next problem. In sedimentation with coagulation, generally the detention period is dash than that of the plain sedimentation. Is it more, or is it less or more or equal? So we have one plain sedimentation without any influence of any coagulant, and then we have a sedimentation with coagulation. So in sedimentation with coagulation, we add some chemicals or we add some coagulants. So these coagulants, so what is the use of these coagulants? Can someone tell me why these coagulants are added? To form flocks. Okay, so actually if we see, plain sedimentation will definitely happen for every kind of particle. However small it is, the sedimentation will happen due to the action of gravity. But many,
Less than the air sedimentation.
yeah, so many a times the particles will be so small that it may take hours or days or even weeks to settle. Okay, so to increase the settling rate of those particles, what we do, we add some coagulants, okay, which destabilizes uh, the particles, and it allows them to come closer to each other and form flocks. Okay, so once it form flocks, what will happen, they will gain in mass. Okay, the size will increase, the mass will increase, and because of the increase in mass, the settling rate will be higher. So if the settling rate will be higher, then the detention period will obviously be less. So a sedimentation with coagulation will definitely have lesser detention period than that of a plain sedimentation. Okay, so the addition of coagulants causes the particles to clump together into larger flocks, which settle faster, requiring less time to settle in the sedimentation tank. Okay, I hope this is clear to all of you. Moving forward, in natural flow conditions, an unpolluted river would likely to have more dissolved oxygen in summer than in winter, less dissolved oxygen in summer than in winter, more or less the same amount of dissolved oxygen in winter and summer, the least amount of dissolved oxygen during floods. So which of them is correct?
think B, sir.
B. Any other answer? So I am getting mixed answers. C, A. So one thing I can ask, so if the temperature increases, whether the oxygen holding capacity will increase or decrease for a liquid? So that is the first question here. If the temperature increases, whether the oxygen holding capacity will increase or decrease?
Decrease.
Decrease, right? Decrease. So what will happen? Now you can answer it.
Less dissolved oxygen in summer than the in winter.
Yes, exactly. So B is here the right answer. B is the right answer because as the temperature will increase, the solubility of the oxygen will decrease. Okay, so that thing you have to keep in mind. So the correct answer is less dissolved oxygen in summer than in winter. Okay, next problem. This is a small numerical. I request everyone to just try to solve it as soon as possible because it's a one line problem. So it says that in addressing the treatment of a daily water flow of 1200 meter cube in vertical direction, a municipal corporation has identified specific parameters for a circular settling tank. The tank's diameter is 10.78 meters, depth of 4 meters. Determine the overflow rate or SOR for this circular settling tank designed for the removal of discrete suspended particles. So we have a circular settling tank and the diameter and depth is already given. The volume of daily water flow is also given, that is 1200 meter cube, okay, per day. So what is the overflow rate or the surface overflow rate, SOR? What is the surface overflow rate? So it's a one line answer. Please try to solve it. I'll wait for some time. 13. Yes, 13 is the right answer. Yeah, 13 is the right answer. For others, I will solve it. So this is question number 4. So first, since the diameter is given, so diameter of the tank is already given, that is 10.78 meters. Okay, so from that we can find the surface area. The surface area of tank. So what will be the surface area of the tank? It will be pi by 4 into d square. Okay, so it will turn out to be 91.27 meters square, something around that, the surface area of the tank. So if the tank is like this, so this diameter is given as 10.78 and height is given as 4 meter. So although for this question the height of the tank is not required. So now the surface overflow rate or SOR will be equal to the Q discharge divided by the surface area. So what is the discharge? It is 1200 meter cube per day divided by 91.27 meter square. So it would be approximately 13.14 meter per day. Or we can write approximately 13 meter per day. Okay. So while calculating the surface overflow rate, you have to be very careful like which area to consider. Okay. So based on the flow of the treatment system, so here we are considering this top area. If it's a rectangular tank, suppose we have a rectangular tank like this, where this is the length, this is the breadth, and this is the height. We will consider the length into breadth sometimes. Okay, if the flow direction is like this, sometimes we will take this area. So we have to see from where the flow is happening. Based on that, ideally in surface overflow rate, we will take the top surface area, that is length into breadth. Okay, so we have to be careful because some extra information like this height of the tank and all will be given in many places. So we have to take care of that. Okay, so let's move on to the next problem. Okay, so it's a statement type. Statement A, microbiological examinations of, yes, Preeti, you want to say something?
Yeah, in the question which you mentioned before, there's the fourth question.
Yes,
It says daily water flow of 12,
yes.
1200 meter cube per day. Per day, is it per day?
Yeah, it's written right, daily water flow. So daily means of for a
Okay,
day. So 1200 meter cube per day. Okay, so
okay,
directly we can
okay,
take it. It's just the
okay,
play with words.
okay,
Okay. Yeah.
okay. Thank you.
Yeah.
Yeah.
Yeah, but that was actually a very good point. So you have to take care of these things. Sometimes the discharge will be given as volume, sometimes as volume per day or per some unit time. So you have to take care of that. If it's a, maybe they might have written 1200 meter cube for a 12-hour cycle, then you have to do it accordingly. Okay, so be careful of that. So next problem, statement A says microbiological examinations of water samples are usually based on MPN test for the detection and enumeration of indicator organisms rather than that of pathogens. Statement B, the identification of pathogens in water is both time consuming and difficult. So which of the statements are true and whether the first statement is the correct explanation of the second statement. So what is this MPN test? What is the full form? Anyone knows? What is MPN?
Most probable
Most
number.
probably
Most
number.
probable number. Yes, that is true. So basically for examining how much, how like quantifying the microbial concentration generally. Okay, so we do the MPN or the most probable number. So it will be MPN per 100 ml. That's how it is denoted. Okay, so I got one answer. What about others? Any other answer?
D.
D. Okay. So, what do you think? If I want to know the condition of my water sample, whether it has pathogens or not, uh, is it always easy to find out the concentration of pathogens? Because those are first of all very deadly or harmful to us. Okay, and the identification of them is also difficult. So what we do, instead of quantifying the pathogens, what we do is we try to quantify some other organisms which are already present whenever the pathogens are present in our system. So So if those organisms are present in our system, we are quite sure that the pathogens are also present. So those organisms are called as indicator organisms. So one of them is like E. coli. Okay, so they themselves are not very harmful. Not all strains are harmful. Few strains may be harmful, but they are used as an indicator organism to quantify this microbiological uh, sample. Okay, so that's why we do this MPN test, or most probable number. So this statement 1 is true, and statement B is also true, and it's a correct explanation because the identification of pathogens are both time consuming as well as difficult. Okay, so that's why we look for the indicator organisms. Okay, so they themselves are not harmful generally. So the most probable number test is a statistical method. Okay, it's not a direct method, it's a statistical method that estimates the number of viable organisms in a sample, and often used to test food or water for coliform bacteria and E. coli. Okay, let me go to the next problem. The figure below provides insight into the variation of city population based on the ratio of peak hourly flow to average flow. Okay, so you have to guess whether AB is a smaller community or AB is a or larger community, and same with BC. BC is a smaller community or BC is the larger community based on the peak hourly flow to average flow ratio. C. Okay. Any other answer? See, so here I would tell you one thing, that there can be more than one answer correct. Okay, so if one is the larger community, other will be a relatively smaller community. Okay, so like that you can answer. So there are two correct answers here. Okay, so here we can see that AB, the ratio of hourly flow to average flow is higher. Okay, so if the ratio is higher, generally the population will be, it will be what? If the ratio is how higher, the ratio, the population would be lower, because generally we say that for lower population the peak hourly flow is generally higher. Okay, so that's why AB denotes a smaller community and BC denotes a larger community. Okay, because the ratio of hourly flow to average flow, that is we call it as a peak factor. Okay, peak factor is generally lower for high population area and higher for low population area, because the fluctuations are less. Okay, is there any doubt in this why it is higher and lower? Then I can explain in a graphical manner. Is it clear? I think because it makes sense, right? Okay, if you have any doubt, you can stop me and I can explain it in a better way. Or else I will move to the next problem. Okay. Okay, I hope this is fine. Next one. In the figure below, identify the type of treatment unit process indicated by the various blocks labeled A, B, C and A, B, C, D and E. Okay, so you have to tell me what does these blocks denote. So please try to answer which of them is correct. C, okay. Yeah, I think now we are getting the correct answer. So it is D. Okay, so the first block, that is block A, it shows bar screen and grit removal. So these are preliminary treatment. Okay, then we have the primary clarifier, which is the primary treatment. Then we have the aeration tank and secondary clarifier. So it is the secondary treatment, while or the biological treatment, whatever. Okay, then we have some advanced treatment or nutrient removal. Okay, so these are generally, these falls under the tertiary treatment. Okay, and then we have gravity sludge thickener, we have anaerobic digester, and we have filter press. Okay, so all these are for the sludge streams. We can see that from primary clarifier and secondary clarifier, two streams are coming, which are basically sludge. Okay, that black dotted line. So these are sludge streams. So this is for a sludge processing unit. So E represents a sludge processing unit. So the correct answer is option D. Okay. Next, what does the presence of free ammonia in river water indicate? Okay, so if there is free ammonia in water, what does it indicate? Does it indicate recent pollution, past pollution, intermittent pollution, or no pollution of water with sewage? A, A, okay. So if it's a recent pollution, so what does happen to this ammonia in the presence of some microorganisms and oxygen with time? What does happen to this ammonia? Because many of you are answering it as recent pollution. It converts to nitrates. Yeah, that is true. So first to nitrite, then to nitrate, and if there are some denitrifying bacteria, then to nitrogen gas. So ammonia, there are various forms of nitrogen, like how it is present in the river water. Okay, so that is why if ammonia is there, we call it as a recent pollution. Okay, the presence of free ammonia in river indicates recent pollution with sewage, as free ammonia is a byproduct of the initial decomposition of organic matter found in the sewage, signifying a fresh influx of wastewater into the water body. Okay, so by the decomposition of any organic matter, this ammonia is formed and it is found in the water body, which gradually can convert to nitrite and then nitrate and then further to nitrogen gas based on the kind of whether it is an anaerobic or aerobic system and what kind of microbials are present in the system. Okay, next. In a water treatment plant, a horizontal sedimentation basin maintaining laminar flow condition is designed to handle a flow rate of 0.45 meter cube per second. The basin has a rectangular shape with dimensions length 42 meter, width 16 meter, and depth as 5.5 meters. Assuming the settling velocity of the particle follows type 1 settling, calculate the removal efficiency of particles. Given the diameter of the particle as spherical of 28 microns, particle density 2.5 gram per centimeter cube, density of water 1 gram per centimeter cube, dynamic viscosity as 0.01 gram per centimeter second, and acceleration due to gravity as 980 centimeter per second square. Okay, so you have to find out what is the percentage of the removal efficiency. So we have a set of data pertaining to the basin, okay, pertaining to the sedimentation tank, and we have a set of data pertaining to the type of particle that are being settled. Okay, so based on those two information, we can find out how much of particles will be removed from the system. Okay, so it's a three-step process. Please try, please attempt. I will wait for a minute or two and then we can discuss. Yes, yes, I will definitely solve this. I'm just waiting for someone to answer. If they are trying, I will solve this and explain the problem. Definitely. Just wait for some time. So it though looks a very big problem, but yeah, it looks a very big problem, but it's not ideally. So in within 2 3 steps we can solve it. Okay, so just take a screenshot of this question. So while solving, you can refer to the values. Okay, I hope you have taken the screenshot. Let's move. So this is question number 9. So we have a rectangular tank. Suppose. Okay, so this is the length. This is the height or
So
depth.
we basically find the like V is by V zero
Yes, yes,
removal
yes,
efficiency.
yes. Like that only we have to do.
So we start with the laminar flow, like
Yes.
Vs equals to G times to
Yeah, yeah.
density.
Yeah, we will first
Um,
find what is the overflow rate. Okay, we will also find with the help of this basin characteristics, and then we will find out the settling velocity based on the Stokes law, and then we will take the ratio of Vs by V naught. Okay, that's it. So whatever you said is correct. So just conceptually, I am just telling you, and suppose this is the breadth B. Okay, so always remember whenever we are finding the overflow rate, we have to take the top surface area. We have to take the top surface area, that is the length into breadth. Okay, so first we will calculate the overflow rate of the tank, and we denote it by V0. V0. So that is the discharge divided by the top surface area, that is length into breadth. Okay, so what is the discharge? It is 0.45 divided by length into breadth, that is 42 into 16. So that is 6.696 into 10 to the power minus 4 meter per second. Okay, meter per second. So this is the overflow rate, V naught. Now, since always remember the Stokes law is valid only for type 1 settling. Only for type 1 settling. So here they have clearly mentioned that the velocity of particle follows type 1 settling. So if it is written, then only we can apply the Stokes law to calculate the settling velocity, or else we have to find some other way. Okay, since the Stokes law is applicable, we can write the settling velocity of the particle. Okay, of the particle, we will denote it as Vs. Vs. So that is, since Stokes law is applicable, that is rho into G into the specific gravity minus 1 into d square by 18 mu. So this is the formula, directly Stokes law. So we will just put the values. Okay, so that is 1 gram per centimeter cube into 980 centimeter per second square into 2.5 minus 1 gram per centimeter cube. Okay, into the d would be 28 microns. Okay, square divided by 18 into 0.01 gram per centimeter second. So here you have to take care of the units. Okay, something is in micron, something is in centimeter. Okay, so you have to convert all those, do those unit calculations, and finally your answer you will get it as 6.403 in 10 to the power minus 4 meter per second. Since here I am calculating in meter per second, here also I should find it in meter per second. So that's why you have to take care of these unit conversions and then solve it. You will get the settling velocity also. Once you get the settling velocity, now the particle removal efficiency will come. So particle removal efficiency, that is nothing but Vs by V naught into 100. Okay, so That is 6.0403 into 10 to the power minus 4 divided by 6.696 into 10 to the power minus 4 into 100. So you will get it as approximately 95.62%. Approximately 95%. Okay, if you see the options, we have, yeah, we have 95%. We don't have 96%, we have 95%. So we will put it as 95%. So first calculate the overflow rate V naught Q by LB. Then calculate the settling velocity only if Stokes law is applicable for type 1 settling. Then we have to do the ratio of Vs by V naught. Okay,
And
so
for settling velocity, if the unit is in meter per second, will it be fine?
yeah, it should be in meter per second. Yeah,
Okay.
yeah. Ideally, so always go for the standard SI unit. Always go for the meter per second. Okay, whatever is given, you convert everything to meter per second.
Okay, thank you.
Yeah. Okay, let's move on to the next problem. So 95% is the right answer. Yeah, same thing is written here. Okay. In the
Sorry.
yeah,
So the gravity it's converted. It's converted to
yeah,
gram
you
per
can take
meter
nine.
square.
You can take it
9.81,
9.81 meter per second square. Yeah, you can take it.
and the diameter is actually 28 into 10 power minus 6. Correct?
Yes. 20 into 10 to the power minus 6 per meters. Okay,
Meters.
that's
Yes. Others don't have. We don't have to convert anything,
no.
right?
Others are also in like centimeter, right?
Oh,
Uh,
gram per centimeter
yes,
cube.
yes. Actually, this density, okay, density is
Density
gram per
is.
centimeter cube. You can take 1,000 kg per meters cube, like that. Okay.
Okay. Okay.
Yeah.
Okay. Thank you.
Okay, so just make sure that first of all you have to memorize these density of water, then the specific viscosity, okay, viscosity, density, and gravity. These things you should remember in SI unit. That is very much important. Okay, so any question
Yeah.
comes, whatever is given in the question, don't worry about it. Whatever you know, put that value in SI unit, and rest, whatever other information is given, convert it to meter second, all these things. Okay,
Yeah.
yeah. Okay, next problem. It says that in the Monod equation, mu represents that substrate concentration at which specific growth rate is half of the maximum, whether it's true or false. So do you know what is the Monod equation? What is the Monod equation? Where we use it? Okay, anyone else? So basically Monod equation is something, so we generally plot substrate substrate S with the growth rate, or specific growth rate mu. Okay, so we say that as the substrate is increasing, the growth rate also increases to a certain point, and then it becomes constant. Okay, so this is the Monod graph, okay, or Monod relationship. So generally it is mu is equal to mu max S divided by Ks plus S. So this is the relation. Okay, so growth rate will increase up to a point, and with respect to the substrate, and then it will be a constant for any bacterial growth or something. Okay, so that's what is generally observed. Now, what is, so this is the, so this level, this is the maximum growth rate. This is the maximum growth rate. Now, what we do at half of this maximum growth rate, suppose here, so that is mu max by 2, we interpolate it and find out what is the substrate required. So this we call it as Ks, or half saturation constant. Okay, we call it as Ks. So this Ks is this one. Okay, so we know we know mu max, we know S substrate. So Ks is half. So Ks is that substrate concentration at which the growth rate is half of the maximum. Okay, so always remember this is half saturation constant. Okay, so this is the inference. So now in the question it is saying that in monod equation u mu represents that substrate concentration at which specific growth rate is half of the maximum. Is it true or false?
False.
It is false because it is not mu, it is Ks. It is Ks, so it is false. Okay, so the same thing. Yeah, same thing is that. Okay, let's move on to the next problem. The municipal corporation must handle a daily volume of 720 meter cube day of water. It is found that overflow rate is 16.5 meter per day, depth is 3.5 meter, width is 5 meter. The length of the rectangular settling tank designed for the removal of discrete suspended particles would be. So what would be the length? So similar problem we have done. So please try to answer. No, it's not around 12.46. I think you have to. Yeah, around 9 meters. Yeah, around 8.73. Yeah, that is correct. That is correct. So how did we get this? So this is question number 11. So first we will calculate the surface area. So what will be my surface area? Surface area will be nothing but the discharge divided by the SOR, surface overflow rate. Okay, or overflow rate. So discharge is around 720 meter cube per day and overflow rate is 16.5. So we'll get something around 43.64 meter square. So once we know the surface area is nothing but L into B. So 43.64. We know B, so L will be 43.64 divided by 5. So it will be 8.73 meters. Okay, very simple. Next problem. The following data are given for a channel type grid chamber of length 10 meter. Q is given, depth, width, specific gravity, all the informations are given. So assuming Stokes law applies, the maximum diameter particle that can be effectively removed with 100% efficiency is. So what is the diameter? So please tell me.
So if we find the V like V equals to Q by A, so Q is 0.75 and A is like 3 times to 10
Oh
length
no, but
into the way.
here they are
So
asking. Here,
0.025.
sorry, I'm not getting your point. Can you?
Yeah, I've said we first of all we should find the V, like V
Correct.
equals to Q by A,
Yes, yes.
and A is like 10 times to 3, Q is
Yeah, yeah,
0.75, V is
yeah.
0.025.
So you'll get the V, then equate it to the Stokes law.
Yeah, and after applying to the Stokes law, we kind of get a number like 0.175.
Yes, yes. It's, yeah, 0.175. That is true. Yeah. So 0.175 mm. Okay. That you will get. Okay, I will solve it for others. So what we are doing here is, so first, if it has to be removed 100%, then the settling velocity has to be equal to the overflow rate. Okay. So settling velocity should be equal to the overflow rate. So for that, first we will calculate the surface overflow rate. So that is nothing but Q by area or Q by L into B. Okay, so that is 0.75 divided by 10 into 3. We will get 0.025 meter per second. Okay, then we will equate this SOR of 0.025 meter per second to the settling velocity, which is equal to rho g minus 1 d square by 18 mu. So all these information are given except the d. Okay, except the d. D is not given. So from here, if you equate everything, you will get d is as 0.175 mm. So you have to find the answer in mm. Okay, you can find everything in meter, then divide by 1000. Just you get it by mm. Okay, right? Let's move to the next problem. So for this numerical type of values, what generally happens is uh, they specify a range. So here, like I have specified a range of 0.16 to 0.19. So generally for the answer, they have specified a range. So any value in between will be correct. because many a times people may take 1000 kg per meter cube as 999 kg per meter cube in some test books or in some places. Okay, and approximation, so error due to all these things will be accommodated within this range. So that's why this range is specified. If there are no chance of any error or something, then the range will be one particular value. Otherwise, for the case like this, there will be a particular range. So any answer in between will be correct. Okay, next problem. Which of the following factors does the sewage load does not depend on? Rate of water supply, population growth, infiltration of groundwater, design of sewage system. Design of sewer system. On what of the following factor the sewage load does not depend on? So actually in this question, if we see ideally, uh, the ideally groundwater infiltration should not be a part of the sewage, ideally. But in many of the cases, due to the seepage of this or infiltration of groundwater, the sewage load changes. Okay, so infiltration of groundwater many a times is considered in the sewage load, though it is not ideal. Ideally, we should have separate pipelines for this groundwater infiltration or surface runoff thing, and separate pipeline for sewage. Okay, but here the option D, that is the design of sewer system, will definitely will not be a factor on which the sewage load depends on. Okay, because design is something that we do after knowing the sewage load. Okay, so that is not a factor on which the sewage load depends on. So once we know the sewage load, based on that we do design the sewer system. Okay, so option D is the correct answer here, because rate of water supply will influence the sewage load, population will increase the sewage load, but design of sewer system will not. And ideally, infiltration should also not be a part of sewage, but in the context of this problem, option D is the correct answer. Okay, next. Select the correct statements regarding screens and their purpose in wastewater treatment. Screens prevent any interference to the treatment. Screens are used to protect process equipment. Screens are a part of secondary treatment. There is no head loss when sewage flow through them. Which of the options are correct? So here again more than one answer can be correct. So please let me know all the correct options. Not one, but all the correct options. So yes, both A and B, because screens prevent any interference to the treatment as well as they protect the process equipment. Okay. So screens are not a part of secondary treatment. They are a part of preliminary treatment, and there is a head loss when the sewage flow through the screens. Okay, so head loss is there. The formula is also given. Head loss is equal to the capital V square minus small, that is the approach velocity, and the channel velocity, both are there, divided by 2g. Okay, we will solve a problem based on that, so don't worry about it. Next, select the incorrect statement regarding the grit removal. In aerated grit chambers, there are no moving parts below the water surface. A grit chamber is usually installed after primary sedimentation tank. Grit chambers are used to remove oil and grease from the wastewater. The purpose of proportional wear at the end of channel type grit removal is to measure the rate of flow in channel. So here again, there can be more than one correct answer. So please answer both of the options. So yes, B and C are the correct option because uh, the grid chambers are usually installed before the primary sedimentation tank, and they are not used for removing the oil and grease. Skimming tanks are used for removing the oil and grease. Okay, so option B and C are incorrect. Next problem. For a grid chamber, when the flow velocity of 0.45 meter per second and the detention time is 45 seconds, so what is the length of the tank? So what is the length of the tank? I think this is very simple problem.
Isn't it like flow times to detention?
Yes,
Length
yes,
of time.
directly. So that is 0.45 into 45 seconds. So it is 20.25. Okay, so flow velocity. So from the units only you can find out. So meter per second into second will give you meters. So that is the length of the grid chamber. So sometimes the question may seem too simple, and sometimes it will be a simple problem, but extra informations will be given, so you have to ignore those. Okay, so here it is direct 0.45 into 45. Next, for a given discharge, the efficiency of sedimentation tank can be increased by increase the depth of the tank, decreasing the depth of the tank, increasing the surface area of the tank, decreasing the surface area of the tank. How can this efficiency of the sedimentation tank be increased for a given discharge? So can someone tell me like why increasing the surface area of the tank will increase the efficiency? How does it relate? So we have solved so many problems again and again using the same formula.
Detention time will be higher side.
Okay. Any other answer? Yes, someone was trying to speak. You can tell me the answer. Like how increasing the surface area will increase the efficiency of sedimentation tank.
More particles will tend to settle if we increase the surface area.
Okay, so but how does increasing the surface area, why do you think more particle will tend to settle? And also remember this is for a given discharge. Okay, discharge is constant here.
Will the retention time increase?
Okay, but how does it like we are seeing one formula again and again, right? So we know that surface overflow rate is equal to discharge by the area, by the surface area. So to increase the efficiency, we have to decrease the overflow rate. So the lower the overflow rate, more particles will be settling. Okay, so based on that formula only it is coming. Okay, so we have to decrease the overflow rate, and to decrease the overflow rate for keeping a same discharge, so discharge is not changing, so q is not changing, so we have to increase the surface area. Okay, now I hope you are able to relate. Okay, here you can see vs v, it should be v naught actually. So v naught is equal to q by bl. Okay, so if I want to reduce the overflow rate, I have to increase the surface area when the discharge is constant. Okay, discharge is constant here. So that is, so many of you will think that okay, increasing the depth will increase the detention time like that, but here it is given that discharge is constant. So we have to take that into account. Next, the peak factor is given by peak flow into average flow, peak flow minus average flow, peak flow plus average flow, or peak flow by average flow. What is the peak factor?
Sir, D. Peak flow divided by average flow.
Yes, yes. So D is the correct answer because peak flow by average flow is called as the peak factor. Non-spherical particles will settle dash spherical particles. Slower, faster, equal, or same. What do you think? Slower. Okay. Any other answer? Faster. Okay. So just uh, consider a spherical particle and a cubical particle. Okay. So what do you think? Which one will be settling faster in the same media? And why? Another question, if I may ask, why? So if you are answering for this problem, I would also like to know why do you think this non-spherical particle will settle faster or slower than the spherical particle? What is the reason?
I'm not sure, but maybe the because of the surface of it.
Okay, so suppose I have a ball kind of thing, cricket ball, and I have a box, cubical box, and I'm dropping, they are of same uh, weight, okay, same specific gravity. So when it will be passing through the media, don't you think if it is more irregular, okay, then the drag force will be more. Okay, the force, the yeah. So spherical particle will face lesser drag or lesser friction kind of say, but the ideal term is drag. Okay, so lesser drag force will be there. Okay, so a smaller coefficient of drag will be there, right? So that's why non-spherical particle will settle slower than the spherical particle. And even in the Stokes law equation, there is another coefficient for the shape of the particle or shape factor. Okay, but generally we don't use it because we are consider all the particles to be spherical particle. But that is not the case ideally in most of the cases. Okay, the particle size will change. So based on the particle shape, we give a shape factor to it. Okay, and then we will incorporate in our formula. So non-spherical particle will face more drag than the spherical particle, and it will settle slower than the spherical particle. Okay, right? Next, the degree of treatment required for the wastewater depends on raw water characteristics, desired quality and possible reuse of treated effluent, state regulated wastewater discharge standards, or all of the above. So this is actually pretty direct. So all of the above is the right answer because how much treatment we have to give to the wastewater will definitely depend what kind of wastewater is coming into our system. Okay, so raw water characteristics and what is the future use of the treated water. Okay, like for what purpose we are reusing it, or what is the discharge standard by the government or the local body. Okay, so whatever is there, we have to take both the things into account and then do the treatment. So all of the above is the correct answer. Sedimentation tanks are an appropriate example of unit process, unit operation, both A and B biochemical process. This is pretty direct. So sedimentation tank are example of. These questions are very easy, so I think we can. So in sedimentation tanks, is there any chemical change or any irreversible change is there?
We just do the biological treatment there.
No, it's sedimentation tank. I am saying about the primary sedimentation tank. It's a physical separation process, right?
Oh yeah.
Yeah. So if the physical forces are applicable, then it's a unit operation. So always remember, if there is a physical force only there, then unit operation. Whereas the activated sludge process and all, where some biological or chemical change happens, so it's a unit process. But this is a unit operation. Okay, this is also fine, I think. Yeah. Intermittent sedimentation tanks. A. Store water for a certain period and keep it in complete rest. Allow water to flow at a reduced velocity for a significant time, are also known as continuous flow type tank, or none of the above. So what is a intermittent sedimentation tank? What is the use? So you just have to guess with respect to the name. So it's an intermittent sedimentation tank. So obviously it will allow to store water for some time in complete rest. So option A is the correct answer. So intermittent tanks are also called as quiescent type tanks. Okay, so it will allow to store water for a certain period of time and in complete rest, not for very high amount of time and not in a continuous type. Okay. Which of the following is not an assumption of Stokes law? Particle settling is independent of the influence of other particles. The medium is of infinite extent. Reynolds number is less than 10, or flow is laminar. Which of them is not an assumption of Stokes law? Which of them is not an assumption of Stokes law? Any answer? So Stokes law is valid only in type 1 settling, right? We know that Stokes law is valid only in type 1 settling. So what is type 1 settling? It is a discrete particle settling. So particle settling is not influenced by any other particle. So this is first assumption. Then medium is of infinite extent. It means that the medium, there is no bound. Okay, so it is freely moving without any influence and of infinite extent. Then the flow should be laminar. Okay, so Stokes law is only applicable when the flow is a laminar flow. And for laminar flow, what is the Reynolds number?
Lesser than 1.
Yes, it should be lesser than 1. So option C is not an assumption because Reynolds number should be less than 1. Okay, so that is the correct answer. So option C is not an assumption of Stokes law. Okay. The surface overflow rate of a settling tank is V. The settling velocity is U. What will be the ratio of removal efficiency of particles having a velocity lesser than the critical settling velocity? So what will be the removal efficiency? So settling velocity is V, settling velocity is U, and overflow rate of the settling tank is V. So what will be the removal efficiency? We have solved a problem like this, right? So we did Vs by V naught, right? Vs by V naught. So what is the answer here? So it should be C. So Vs is settling velocity, which is denoted by U here, and V naught is the overflow rate, which is denoted by V here. So U by V. Okay. So for a given flow rate Q, particles having U greater than V, okay, or equal to the surface overflow rate will be completely removed, while the remaining particles will be removed in the ratio of U by V. Okay. Next, what type of settling most likely to occur in a real sedimentation tank? So ideal, not in ideal case, in a real sedimentation tank, what type of settling do you generally see? So ideally, the settling should be discrete particle settling, right? Okay, in most of the cases, ideally, it should be discrete particle settling. But in reality, in real sedimentation tank, what do we see? What type of settling do we see? Is it compression zone or flocculant? We can take a guess. What do you think? So compression settling will happen only if there is a very high concentration, right? So, so let's not discuss about that because it's not mentioned that the concentration is very high here. Then the other two are zonal and flocculent. So generally the suspended particles in any sedimentation tank, they tend to agglomerate with each other. They come closer and they will form some flocks. So ideally it should be discrete particle settling, but in reality we see a flocculent type of settling. Okay. Yeah, so they have a natural tendency to agglomerate with each other. So that's why flocculent type of settling is more prevalent. Okay, another small numerical. Surface loading rate of a 0.02 millimeter particle is 0.02 centimeter per second. Compute the efficiency of removal of 0.024 mm particle. Okay, this is a very good question. So tell me. So surface loading rate is 0.02 centimeter per second of a particle of size 0.02 mm. So what will be the removal efficiency of a 0.024 mm particle? Please try it out. This will clear many concepts. Anyone who would like to try or take a guess, or you can tell your thought process. How do you want to solve this problem? Any idea? Because we are talking a lot about overflow rate, the settling velocity, everything we are talking about. So here surface loading rate is given, particle diameter is given, and it is asked for another particle diameter. So how do you think we will approach this problem? I will give you one hint. No calculation is required for this problem. Zero calculation is required. You can just see and tell the answer. Any idea? How B is the correct answer? Can you explain?
Like we have D as to be 0.02 centimeters per second, and the V naught is like 0.024.
V naught, is it V naught? It is a particle size.
Okay. Um, okay, can you give us some hint?
Would the
If you
surface loading rate be the same for both?
okay, yeah. So the thing is, the surface loading rate is given, right? 0.02 centimeter per second. So that means any particle, okay, of 0.02 mm will be removed 100%. Okay, so surface loading rate is given. So the particle of that particular size will be removed 100%. Now the question comes, what about a particle of a greater size? So obviously, if 0.02 mm particle is removed 100%, then a bigger size particle will be removed, right? If it is a smaller particle, then we have to calculate, okay, we don't know whether it will be removed fully or not. But surface loading is rate is defined for a particular particle. That means that particle will be removed 100%. So if we have a particle of a greater size than that, the weight is increased. Okay, so weight is increased means settling will be faster, right? So that means that particle also will be removed 100%. Am I making my point clear? Okay, so always remember, if surface overflow rate is defined for a particular particle, that means that particle will be removed 100%, that size particle. If it is more than that, then also those particles will be removed 100%. But if it is less than that, then we have to calculate it. Okay, I hope. So that's why there is no calculation required. The answer is 100%. Next, match the target pollutants with the wastewater treatment units used. Large floating matter, suspended inorganic matter, suspended organic matter, dissolved organic matter. Yeah, that is correct, option C, because it is very direct. So any type of large floating matter will be removed by the screens. Okay, if we have inorganic matter suspended, like some sandy particles or some silt, okay, so that will be removed by the grid chamber. Okay, and if we have organic suspended particles, then we have the primary clarifier for that. And if it's a dissolved organic matter, then some trickling filter or activated sludge process, this type of things can remove. So option C is correct. Next, which of the following is not an objective of providing an equalization tank during a sewage treatment? Okay, so balance the fluctuation in the flow of sewage, balance the fluctuation of concentration of sewage, assist in self-neutralization, removal of organic material. So D, definitely equalization tank. It is very simple and direct. Equalization tank doesn't help in removing the organic matter. Rest of them are correct. Next, a bar screen is installed in a wastewater treatment plant receiving a daily peak flow of 50 mld. Estimate the head loss in meters through the screen, considering the desired velocity of flow through the screen as 0.8 meter per second and approach channel area as 0.86 meter square. Okay, so please try to solve. It's a little lengthy problem than the other. I would not say lengthy, but more steps are there than the other problems. So please try to solve. I will wait for 2 minutes and then we will see the answer. So we have two, three more problems. So just we will finish it off quickly. So just to give a overview of this problem, like what is actually happening here is that this is question number 30. So suppose we have a channel and some bar screens are there. Okay, and so water is moving in this direction. Okay, we are looking from sideways, and if I am looking from the front, so bar screens will be looking like this. So some bars will be there. So these are the bars. Okay, this is the side view. This is the front view. Okay, so they're saying that the Q is 50 mld, that is the discharge, and they're asking what is the head loss. Okay, now velocity through the screens. So there will be two kind of velocity. One is the velocity in the channel. Okay, one is the velocity in the channel, approach channel will be denoting as small v, and there will be another velocity through the screens, that will be capital V. Okay, so which speed do you think will be higher, capital V or small v?
Small v?
Why? See, always remember here also the mass conservation will come into the picture. Okay, so same amount of fluid should flow through a particular area or place, right? So if I am decreasing the area, whether the velocity will see, suppose through the screens the area of the flow is decreasing, right? Because the bars are coming, so area is decreasing. So if area will decrease, what will happen to the velocity?
It will become
It
more
will
higher,
increase. It will,
much higher.
yeah, it will become higher because the amount or mass will be conserved here. Okay, so if area is increasing, so always remember velocity into area, this component will remain constant. Okay, this component, what is velocity is mass meter per second into area is meter square. So it will be meter cube per second. So that means the discharge should be constant. Discharge is not changing. Discharge should be constant. So whenever there is a flow through the screens, the velocity should ideally increase. So this flow through velocity is given as, I think, 0.8. 0.8 per meter per second, and the area of the channel. Okay, suppose denote the uh, I denote the area between the screens as A. Okay, area between the screens as A and area in the channel as small a. So this is small a, this is capital A. Okay, so now let's solve this. So first of all, we have to find out Q. Q is 50 mld, or I can write it as 50,000 meter cube per day, and I am changing it to meter cube per second. So it will be 0.5788 meter cube per second. So I am calculating everything in terms of meters and second. So meter cube per second. Now V, that is the velocity through the screens, is 0.8 meter per second. It is given. Okay. So what will be my A? So what will be my A? A will be equal to Q by V. A will be equal to Q by V. So 0.5788 divided by zero point 0.8. So it will be 0.72 meters square. Right? Now another area A is given. Small area A is given, that is 0.86 meters square. That is given. Okay, so here we can see that the approach area is greater than the area through the screens. So that's why it is 0.86. So it is given. So now I have to calculate the approach velocity. This V I have to calculate. This approach velocity I have to calculate. So what will be? So as I told you that discharge will be constant. Okay, so A into V will be equal to A into V. Okay, so this is constant. So I can write small v will be equal to capital A into V by A. So that is 0.72 into 0.8 divided by 0.86. So this will be 0.67 meters per second. So you can see it was velocity through the screens was 0.8 and this is 0.67. So this is smaller. So through the screens, the velocity will be always higher. So if you solve like this, you will have an idea whether you are solving it as correctly or not. If you get this particular value more than 0.8, that means you are doing something wrong. Okay. So like this, we can cross check our values. So now once we get this small v, so what will be the head loss? Head loss will be equal to 0.0792, okay, into capital V square minus small v square. So 0.0792 into 0.8 square minus 0.67 square. This is 0.014 meter. So this is the answer. Is it clear to all of you? Okay. I hope this is fine. We'll move to the next problem. A grid chamber of dimension 12 into 1.5 into zero point 0.8 and liquid and 0.8 of liquid depth has a flow of 720 meter cube per hour. So what is the surface loading rate and the detention time? So surface loading rate and detention time they are asking. So very easy actually this one also. So this is 31. Okay. So what is surface loading rate? Again and again Q by LB. So Q is 720 meter cube per hour and LB is 12 meter into 1.5 meter. So that is 40 meter cube per hour per meter square. But the units are not like this. The unit should be 40,000 liter per hour per meter square. The units are given in liters, so I can mark it 40,000 liter per hour per meter square. Next one, what is the detention time? So detention time T is equal to the volume by discharge. So detention time is always volume by discharge. So volume is L into B into D divided by discharge. So that is 12 into 1.5 into 0.8 divided by 720. So you will get something around 0.02 hours or 1.2 minutes. 1.2 minutes. Okay. So this is the answer. I hope this is clear to all of you. Next. Calculate the settling velocity of a particle having radius this and specific gravity, assume viscosity. So this is very simple. I think you don't have to go through this again. Okay. So this is very direct, very easy problem. So I think we can skip it for now. Okay. Particle concentration is high and they remain at fixed position while settling. Such type of settling is 1, 2, type 1, 2, 3, 4. Please answer. What is this type of settling? So actually, see, both type 3 and type 4 will have high concentration. Okay. So just by seeing high particle settling, actually I should have told you this much before, but both type 3 and type 4 will have particle concentration as high. Type 4 very high, but type 3 also high. Okay, but the other point is they remain at fixed position while settling. Okay, so they settle as zones to each other. Okay, in zone. So that's why it is a type 3 settling. Okay, I can understand if you are confused with type 3 and type 4, but in type 4 the compression happens. Okay, while set up because the concentration is so much that they first settle and then compress each other. Okay, because of this high concentration. But while in zone settling, okay, they settle in zones, so they remain at fixed position with each other. So that's why this is of type 3. Okay, the last problem for today. The average flow in a municipal wastewater treatment plant is 4,000 meter cube per day. Determine the approximate diameter of the circular primary clarifier to remove the suspended solids at an average flow. Assume the overflow rate is 20 meter per day and the depth of 3 meter. This is very simple. I think first problem was like that. So quickly solve this problem and tell me the answer. So flow is given, overflow rate is given, and depth is also given. So what is the diameter of the clarifier? Whether we need the data of depth, depth is required to solve this problem. Can someone tell me? So this is also very simple. Directly we have done so many problems. Q is given 4000 meter cube per day. Okay, so what will be the area? Area required. Area required will be Q by SOR. So that is 4000 by 20. So 20 meter square. So pi by 4 d square is equal to 200 meter square. Sorry, 200 meter square. So my d will be 16 meters. Okay, very simple. Directly we can do. Okay, so that's it from my side for today. Uh, I think these were the concepts that I wanted to discuss, and I hope you are able to understand. Is there any problem in understanding this problem? Are these problems too difficult for you, or the level is fine? Can you give some feedback?
The level is fine, sir. Is it doable?
Okay. Any other feedback you want to give so that I can improve in the other classes? Any other suggestions or requirements from your side? Because this
Sir,
is
how do I get this PPT and is this
yeah. So
lecture got recorded?
this is getting recorded and it will be uploaded in my YouTube channel. Okay, so I will just write it the channel name. Okay, so it is Akash Saha NPTL. So after the class it will be uploaded. But rather than seeing the video, I would request you please attend the class. That will be more fruitful. So if you have any doubts, you can ask me then and there.
Okay, thank you, sir.
Okay, anyone else, any other suggestions from anything or any feedback, whether the class is fine or okay or you need some improvements, please let me know, because I am there to help you for this course. So please utilize the opportunity. Anything you want to say? Thank you. So we'll meet again next Tuesday, 7 to 9 p.m. Thank you. Thank you, Preeti. So on 17th, we will meet again.
Thank you, sir.
If you have any queries, you can put a mail. Yes, you want to say something?
Good. Good, sir. This is thanks. Good.
Okay. If you don't have any other query, you can leave the session. That's all from my side for today.
Sir, I just had one question. Are these exams for NPT? I mean, exams conducted by IIT given to students who are in abroad, or is it are there exam cities? Because I saw that when I registered for this, when I want to register for the exam, there is an option called other, but they don't say if it is in a particular city in abroad, like for example in the US.
Okay, in US, actually, I don't know. I'm not sure. I have to check with it. So you are asking whether exam centers are there in US also?
US, yeah,
Okay, exam center. I might have to check. Okay, I will get back to it in
sure,
next class. I'm not sure
yes,
because mostly in Indian cities only they are conducting, but they
yeah.
might have started because during my time it was not there. But now I don't know. Maybe while filling the form or during because you have to register it separately for the exam also, right? So
Yes.
while
So there
registering,
are exam centers in UAE,
yeah,
but there is an option called other. But I don't know if the other means it's in the US or not, because I'm not sure if they will give for one candidate, or maybe they are looking
yeah.
for more candidates or
Yeah,
something
yeah,
like
maybe
that.
if
So
more and more candidates. So, so I will try to find out if I get any uh, information regarding this.
information,
I will mail you. Okay, I think I have
sure.
your mail ID, right? Yes.
Yes, sir.
Okay,
It's Preeti G John P.
okay, okay. I will
Okay. Thank you,
mail
sir.
it to you. Yeah, thank you.
Sure. Thank you, sir.